to be the nutrient broth. It could be something else. Yeah. Yeah. So at any rate, you start out with your 100% reading, and then you go ahead and put the bacteria in. Well, I myself, when I used to do this, I never worked with bacterial cells. So I was always doing DNA or proteins. That works too. So DNA or proteins or bacteria, either way, you've seen the broth. So it gets all cloudy in there with the growth. Again, it could have been DNA or proteins, could be the bacteria. It gets all cloudy. So now when you shine the beam is going to hit all these particles. And the light scatters. The light bounces off all those particles. It's called the Tyndall effect.
No.
Give me a minute. The Tyndall effect is named after, surprise, Mr. Tyndall. And this is simply the effect of the light scattering, bouncing off all these particles. So what that means is that the light actually hitting that light-sensitive material, the light meter, is no longer going to be 100%. A lot of it's going in some other direction. So now maybe it's 40% of what you started out with. See, that can be measured. Now, what you do beforehand, I kind of skipped out that part, but what you do beforehand is you make up a series of tubes. That's why you have lab techs, so they can do it for you. Make up a series of tubes with different concentrations that are known concentrations. And then you put those in there, so you see how a certain concentration will have 20%, certain concentration has 40 or 60 or 80, and so on. So you make up a set of standards. And then, when you actually get your digital reading, you know what your concentration is. That's commonly done. It's the kind of stuff I used to do and other things like it. That, again, were digital readouts. No color was required. Now, if I ask you about that on the midterm, just saying turbidity method would be fine. Spectrophotometer, most people don't like the word. Turbidity would be fine. By the way, the Tyndall effect, actually we see it all the time, every winter. You know, when you're out driving on a winter night, cold, and it might be foggy, so you turn on your headlights, and all you see is a white blanket. You know, you can't see anything. We're not seeing anything because of all the fog particles. The head beams are bouncing off the fog particles. So what you're seeing is the scattering of the light. That's a Tyndall effect. And the reason that fog lights point straight down on the road is because that minimizes the scattering of the light. Not really sure how much it really helps, to be honest. At any rate, that's the one normal life experience that we've had with Tyndall. So turbidity method is one of the methods used to estimate bacterial growth. Do you have any questions on that? Is that okay? Okay. The second one, and again, I'm taking it straight from the book, metabolic activity. Actually, we've done that one before. You have some kind of reaction going on. A plus B going to C plus D. And then you just take out a sample every few time units, every few seconds, every few minutes, and so on. It varies. So we'll say every few minutes. You take out a sample, and then you measure the concentration. So if you're measuring products, well, the longer the reaction runs, the more product you should be getting.
It's like what we did up.
It's exactly what we did, yeah. You could measure reactants. In that case, it should be going down because you're getting fewer and fewer reactants. And in terms of biological stuff, you could measure the presence of oxygen. That should be decreasing. You could measure the presence of carbon dioxide. That should be increasing. You get the point. So you can just measure different things as time goes on. And that will give you an estimate of bacterial growth. Third one, dry weight. This actually is my least favorite. When I was still doing research, I could never make it work. You know, a lot of other guys could. I just couldn't. What it is, you take out a sample every few minutes or whatever. So once again, every few time units. Take out a sample, but this time you take out the water. You do that by applying a suction to it over filter paper. You apply a suction to it, you suck out the water, and then you simply weigh whatever's left. That's your dry weight. The problem I had with it is that if I did that, and I suck out what I thought was all the water, if I came back a few minutes later, if I did it again, I could usually suck out more water. I usually never got all of it the first time. So in other words, my measurements would change. And also, the more growth you had, the tougher it became. So you've got your filter paper. So at first you'd have kind of that much, and then a little bit later, you have that much, and then, so you're getting more and more sample on the filter paper as you're waiting longer and longer. Well, the more sample you have, the harder it is to suck out the water. So I never found it to be very accurate. And you know, everybody always has their favorite methods and their least favorite. This was definitely my least favorite. I never did it, unless I had to. But still, some people do use those. So all of these are different methods for estimating bacterial growth. I personally think the spectrophotometer is the best one, but I'm sure other people disagree. Any questions on any of those? Okay, one more to present to you. And this is back on page, again on my book, page 179. It's the growth curve. So just 6 pages earlier in your manual. Again, my page numbers are probably different than yours. 6 pages earlier, looking at the growth curve. So what we're going to do is we're going to add bacteria to a growth medium. So we'll start there. We have some number of cells. So we're adding bacteria. Some number of cells to the growth medium. And we're starting at t equals 0. But again, the number of cells is some number of cells. You measure the concentration by methods we just talked about. Now what's going to happen then for a while is nothing. Because when you first give food, usually you don't use it right away. You've got to digest it, you've got to break it down, then you can start using it. So usually, there will be some period of time, ballpark figure about a half hour, could be 20 minutes, could be 40 minutes, but somewhere around a half hour. It's called the lag period. Lag period. The lag period means you've added it to the medium, but nothing's happening yet. Remember, what we're measuring is the number of cells. The number of cells hasn't changed yet. And then, after about half an hour, then the cells start to divide. You're starting to get more growth now. So, the number of cells starts to increase. Now, the steeper the slope, the more cells you're getting. I found out a couple of years ago, not everybody actually understands that. So if the slope is like that, you're not getting as many cells as if it's like that. But to me, I thought it was pretty obvious, but apparently to some students a couple of years ago, it wasn't so obvious. So, at any rate, so you're getting more and more cells. Now, it turns out this is a logarithmic. Logarithmic growth. In fact, the book, the manual, I wish it didn't do this, but the book, sorry, I interrupted myself. I call it the growth phase. The book calls it the log phase. I wish it didn't do that. I prefer the growth phase because the cells are growing. Now, what logarithmic means? You don't need to worry about solving, don't worry. But what it means is that the rate of change does not change. I'm sure that helped you a lot. So, the cells are going to start to double, go from 1 to 2, 2 to 4, 4 to 8, 8 to 16. That's logarithmic growth. The rate of change, which is doubling of the cells, it doesn't change. It keeps doubling. That's logarithmic. So 32, 64, 128, that's logarithmic growth. So the growth phase is logarithmic. Now, obviously, it can't do that forever. I mean, nothing can go forever. So sooner or later, it flattens. It flattens out. This is called the stationary phase. The stationary phase. During the stationary phase, the numbers are no longer changing. That's why it's stationary. But it doesn't mean that you're still not making new cells. You are. You're still getting new cells. The difference is you're running out of food. So you're running out of food, so some cells are dying. And also, after all, you've got a lot of cells there. Excuse me. You've got a lot of cells there now, so they're making waste products. So basically, you're making new cells, you're also killing cells. That's why it's stationary. And finally, of course, you really do run out of food. There is no more food. And there's lots of waste products, so the cells really do start dying. But this time, there's no new cells coming in. That's the death phase. That's the death phase.
They're dying because they have no nutrition.
I'm sorry, what?
They're dying because they don't have like sustenance.
Correct. And no food, plus they base that poison in the system, all of the waste products. So no food plus the waste products, which are poisons.
What's the waste product?
I'm sorry, what? Well, I mean, for us, feces, carbon dioxide.
That's what.
Well, bacteria have waste products too.
So just to clarify, in the stationary phase, the amount of growth is equal to the amount of
Yeah.
death.
Yeah. The amount of new cells equals the amount of dead cells. So the net change is 0. And then here, there are no new cells. So the cells just die. Now this is also logarithmic. The death phase is also logarithmic. So we have two phases that are logarithmic, the growth phase and the death phase. So we have two phases that are stationary, but one is called the stationary phase. The other is the lag phase. In both cases, no change in the numbers. The difference is that for the stationary phase, you are getting new cells. It's just that you're losing some too. For the lag phase, no new cells, no dying cells. There is no change. Yeah, no, nothing. Any questions on anything? It's just not a bad chapter. I mean, it's not really interesting. That's a different issue. Except for oxygen, it's really not a bad chapter, and you really shouldn't have much trouble with it. One more to go.